And we're back. Welcome back and happy Tuesday. Today, we will pivot to a new topic that's very important to machine learning. Well, they all are. But this one, overfitting, I'd say is among the top 10. But before we begin, some administrative bits. The reading, logistic regression, section 3.3, pages 88 through 99. Neural networks, there's a supplementary chapter. PDF for that is on the course Blackboard site in the course resources section. Overfitting, today's topic, section 4.1 in the main text, pages 119 through 126. So why don't we begin? Where we last left off, we talked about backpropagation, and we developed an expression, delta, for the jth node in layer L, and that represented the partial derivative of the error with respect to the score for node J at layer L. We did this for the final layer, and then worked our way backwards, trying to compute that delta function for the previous layer just beneath that output layer, that jth layer. In developing that expression, we found that we had all of the pieces we needed as a consequence of the forward pass through the neural network, except for delta from the layer above. And that delta from the layer above is backpropagated through the network from layer J to that layer I, the L-1, node I, right beneath it. Hence the name backpropagation. So then we covered our backpropagation algorithm. We, through a series of rounds, we select some nth input and compute the forward pass for that input through each of the layers, layer 1, 2, 3, up to and including layer big L, which is the output layer. And then we compute the backwards pass, computing all the deltas in order from the output layer going back through the network one layer at a time. And then we update our weights using our step size and the gradient that we compute in this fashion. And we keep iterating until our convergence criteria is reached. Either we've expended some number of rounds or we find that the error does not change very much. All right. So let's continue on to overfitting. Now, what exactly is overfitting? Suppose we have a quadratic target function, our blue curve, and for this target function, we're going to also include noise. And we're going to sample 5 data points from this target function. Here's our first data point. Here's our second data point, third, fourth, and fifth. And we're going to add noise to these samples. And this noise is going to tend to either slide them up or down by some amount. And then let's imagine then, given this data, and the scenario is usually you don't see the target function, but we're showing you the target function just for the sake of our argument we're trying to make. So we have our 5 data points sampled from our noisy target function, our quadratic, and we're going to fit these 5 data points using a 4th order polynomial. That's our red curve. And if we did this fit, we get something like the following. And that 4th order polynomial has a higher degree, more degrees of freedom, so it can bend and twist and fold itself suitably in order to exactly fit each one of those 5 many data points sampled from the noisy quadratic. And we'd find that in-sample error is 0. As you can see, it precisely pierces each one of these data points, our red curve does. But if we look at out-of-sample error, the differences between those parts of our target function outside of the sample set, or out of sample, that corresponds to the differences between the blue curve and the red curve away from these sample data values, or in-sample points. And so this out-of-sample error is quite large. If you were to add up all those differences, it's quite a bit of difference. And so this overfitting deals with fitting the noise, not just the signal in the underlying target function. Suppose you have a neural network and you're trying to fit this neural network, learn, as it were, from noisy data. Now, in this, if we run our forward pass, backward pass, forward pass, backward pass, some number of epochs or rounds, and we were to set aside data to mimic our out-of-sample error, and we have our in-sample points, our training data, and we measure in-sample error, which is the green curve, we could depict our out-of-sample error, which is the red curve. Now, if we continue to plot in-sample error and out-of-sample error at each one of our iterations, we would see at some point E in goes down, E out goes down. Okay, everything's inequality, says they track with one another. That's good. And at some point, we reach a point we mark here where in-sample error continues to decrease, but out-of-sample error begins to increase. And so this point, this marked by this blue line, that is the point where overfitting is beginning to happen. Now, if you could only recognize this point and stop and output the current version of your neural network hypothesis, working hypothesis, as our final best hypothesis, that would be the ideal situation. And so the more epochs you run for training the neural network, the more you explore different parts of the space of weights, i.e. your hypothesis set. So noise is the culprit here. And overfitting means that you're fitting the data more than necessary. Now, what happens in overfitting is that your hypothesis and your learning algorithm, as it searches through the space of hypotheses, is treating this noise as if it were a viable pattern. So let's take this example of a snow pattern on a screen. And as you can see, this is just noise. But when you're overfitting, you're kind of hallucinating, looking at that signal pattern, hallucinating a pattern. So for example, let's say if we looked over here, well, this almost looks like part of a bird. So there's the head of the bird, there's the beak, there's the body, and the bird's sitting down. Its wing is folded here, there's the eye. That looks like a bird. But it's just noise. And so the noise is the culprit. And your model, when it overfits, it's hallucinating a pattern from this noise. And then when it goes out of sample, it's out of sample data, it still thinks that that hallucination, as it were, is an actual pattern when it's not, and you get a dramatically large out of sample error. So the noise is the culprit. And so when you overfit, you're treating noise as if it were a real or viable pattern, and then you're discerning this noise pattern that doesn't really exist out of sample, and you have a large out of sample error. So fitting a noise in your data is harmful to your out of sample error. Now, overfitting is not the same as bad generalization. Bad generalization refers to a hypothesis, inability to bend and twist and fold suitably enough to keep up with the ground truth target function. Overfitting is the extrapolation of the noise pattern to your out of sample data. So the two are different, but they manifest themselves in an identical way, and we'll talk about what I mean by that. And so here's an example, and let's imagine we had two target functions. We have a 10th order polynomial with noise, so you're going to perturb those points you sample from a 10th order polynomial. And you also have a 50th order polynomial that's very wiggly, a lot of degrees of freedom, and that 50th order has no noise. And so let's imagine then we took 15 samples from each one of these, the noisy 10th order polynomial and the non-noisy 50th order polynomial. So the goal then is to fit two different hypotheses to these two different target functions from which we are sampling 15 many samples. And so we're going to fit a second order polynomial, and we're going to fit a 10th order polynomial. And so if we were to do this, okay, this is going to be our fit for the data. Here we have our noisy data. That's going to be our 10th order polynomial, and we're going to add noise to it. And then our complex non-noisy 50th order polynomial, this is going to be what that 50th order polynomial looks like. It's a lot more wiggly on the right. And we sample 15 data points from this non-noisy target function. You can see that all of these points are on the 50th order polynomial. So on the left here, we have the 15 samples from the noisy 10th order polynomial target function. And on the right, we have the 15 samples from the non-noisy 50th order polynomial. Okay, and so let's take a look at the two fits. Now, remember, we're fitting a second order polynomial and a 10th order polynomial to each. So on the left-hand side, we have the noisy low order 10th degree polynomial, 10th order polynomial. And if we look at in-sample error and out-of-sample error for both of our hypotheses, well, the second order polynomial, it has an in-sample error of 0.05, out-of-sample 0.127. If we look at the 10th order, well, the 10th order is the same order as this noisy 10th order ground truth target function. And if we look at in-sample error, gosh, well, it's smaller. In-sample order for the 10th order hypothesis set is 0.034. It's smaller. But if we look out of sample, that's pretty bad. It's 9. It's much, much, much bigger, order of magnitude bigger, in fact, than the degree 2 polynomial hypothesis set. And so that is the case because the difference between the 10th order hypothesis set and the 10th order target function is the noise. And this noise is impacting our out-of-sample error for that 10th order, even though it's the same degree as this unknown target function. So let's take a look at the noiseless high-order target function. That was the 50th order polynomial. And again, we're going to fit with a second order hypothesis set and a 10th order hypothesis set. For the second order, we get in-sample error of 0.029. Out-of-sample error, we get 0.120. Now, as much as we try, the second order polynomial is going to try, it does an okay job, but it can't quite bend and twist and fold suitably enough to match all the placement of the data points from that noiseless 50th order target function. And that's the green curve here. Now, if we look at our 10th order, well, the 10th order has more degrees of freedom, and it's going to bend and twist and fold and try its best to match all of the bends and twists and folds inherent in that 50th order noiseless target function. And it's successful. And if we see here, it just about pierces this red curve, or 10th order hypothesis set, just about pierces every single data point sampled from the noiseless 50th order target function. So if we look at in-sample error, it's 10 to the minus 5. It's very, very small, far smaller than the second order. But if we look at out-of-sample error, it completely blows up. Over 7,000. That's huge. And again, there is no noise here, but we got a high out-of-sample error. And this was because even though the 10th order polynomial can bend and twist and fold quite dramatically, it can't quite keep up with this 50th order noiseless target function. So it behaves the same as if there were noise. So we have our two learners, and they both know, can imagine if they knew, that the target function is a 10th order polynomial with noise, and you had 15 data points. So let's imagine that. And we have two learning algorithms. Learning algorithm 1 is going to choose second order polynomial fit, and algorithm 2 is going to choose a 10th order. And so what we want to do is then compare these two learners to look at the behavior of when this poor out-of-sample error happens, this overfitting happens. And we're going to look at that from the perspective of a learning curve. And so here, on the left-hand side, we have the second order polynomial, and we see that the expected error is going to be relatively large for in-sample error. And that is certainly the case because this second order polynomial doesn't have the degrees of freedom to bend and twist and fold and keep up with the bends and twists and folds of that degree 10 polynomial, but it also is subjected to noise for that noisy degree 10 polynomial. And so in-sample error is going to be larger, hence this gray area for En is going to be much larger. And we can see, of course, as we increase the number of data points, out-of-sample error is going to approach in-sample error. And then if you have enough, it does okay. And here we have both noise as well as this degree 2 hypothesis set H2 not being able to keep up with that degree 10 polynomial. So if we look at the other example, we have in-sample error starts really small because you have a degree 10 polynomial as your target function, and you also have a degree 10 polynomial, H10, for your hypothesis set. It can represent that target function really well. Of course, we said before the difference is noise. But because it can represent it very well, before you even have a large number of data points, you see that En is relatively small. Granted, as we said before, you match the complexity of the hypothesis set to the data resources and not to the complexity of the target function. But nonetheless, we still have the degrees of freedom in our hypothesis set H10 to represent at least the bends and twists and folds to keep up with this noisy degree 10 polynomial target function. And as we see, the expected error for out of sample is quite large. And the reason for that is because when we're fitting with H10, we're also going to fit the noise. And so eventually, if the number of data points got really, really big or big enough, then H10 would absolutely be the clear winner. But H10, when we're choosing a hypothesis set, as we said earlier, you match the complexity of the hypothesis set to the data resources and not to the complexity of the target function. And because our target function has noise, when we're fitting, H10 is using its degrees of freedom to hallucinate a pattern from the noise. And it pays for that with poor out-of-sample performance. Okay, so let's now think about the two learners. And our hypothesis sets, H10, degree 10 polynomial, and H2, degree 2 polynomials, can't really know about noise. Now, of course, when we had a high degree polynomial, 50th order target function with no noise, and we tried to learn the samples from this high degree target function with no noise, it acted a lot like what would happen when there is noise. So one of the things we're going to look at is how the noise level in the target function, along with its complexity, impacts this poor out-of-sample performance due to overfitting. And so let's instrument things a little bit more neatly, and we're going to build a target function in a normalized fashion, and we're going to build it so that we can control precisely the complexity marked by the degree of this target function. And so we're going to use the set of Legendre polynomials. It's another method for representing polynomials, and it's normalized between +1 and -1. And doing so allows us to specify our noise parameter, sigma squared, as a z distribution or a standard normal distribution, and it will be meaningful as we set this noise. Moreover, this Legendre polynomial, it is a polynomial, and we can collect together all of the x values raised to an exponent, and the resulting coefficient we get, we're going to call them our alphas. And so here we can represent our polynomials in this alternate form that also gives you more interesting polynomials versus things that are just variations beyond degree 2. A third order looks like this. Fourth order is just a little steeper. Fifth order is a little steeper. You have a lot more variation and interesting bends, twists, and folds when you represent as this Legendre form. And so let's imagine now in an experiment where we will vary the complexity of the target function by changing QF, the term representing the different powers of x in Legendre form, as well as sigma squared, the noise process. And so sigma squared is 0. It's going to be noiseless. As sigma squared increases, it's going to increase the variability selected by the z distribution, the standard normal. All right, so we can alter the noise level through sigma squared. We can alter the target function complexity with this QF, which is the term bound for the summation, which defines the Legendre polynomial. And then we can also control the data set size. Now, of course, when we run this, we're going to look at the performance between two different hypothesis sets. One we're going to call the high order hypothesis set, degree 10 polynomials, G10, H10, and the low order hypothesis set, the degree 2 polynomials, H2. Now, of course, we input our data set, our label instance pairs, and many of them, that's our data set size. And as a result of convergence of our learning algorithm, we get a final best hypothesis G10 and a final best hypothesis we're calling G2 from our hypothesis set H10 and H2 respectively. And so if we're going to look at our overfitting, we're going to represent that as the difference between out of sample error on our high complexity final best hypothesis and our low complexity final best hypothesis. So here we're going to represent the difference between E out of our high order final best hypothesis and E out of our low order. And so if this expression is positive, it means that we're overfitting, because it means E out of G10 is greater than E out of G2, meaning G10 is more complex and it overfits, and we get a bigger difference. If this value is negative, it means G10 is not overfitting. All right, so let's take a look at this graph. We run this experiment, and on the left-hand side, we fix the complexity of our Legendre polynomial, our target function polynomial, to 20, and then we're going to vary our noise process sigma squared. So here along the horizontal axis, we have the number of the data points, our data set size, and then here on the vertical axis, we have the noise level. And how this goes, if E out of G10 minus E out of G2 is positive, that means we're closer to red up here. Otherwise, if it's 0, we're here, green. And if it's negative, we're blue. So it's kind of heat mapped. And so let's see what happens here. Now, of course, if we have a very small number of data points, we are overfitting. We have in the red here, the difference for no noise level between G10 and G2 is very large. And if we increase the noise, we go up, it still remains the same. Now, as we go to the right along the horizontal axis, we increase the number of data points. And if we increase the number of data points enough, we're not overfitting with G10. But if we increase the noise, say from a data set of size 10, we go up. Eventually, as we increase the noise level, G10 begins to severely overfit. And so if we increase our data set size really, really big, going over here around 140, 160, you see that we can tolerate a lot more noise before we start to overfit as we go on. And so the other experiment we try, we want to look at, and this is on the right-hand side, the impact of complexity given a fixed noise. And so we're going to fix our noise sigma squared to 0.1. And here along the horizontal axis, we have our data set size. On the vertical axis, we increase our target complexity. That's 0. That's 25. This is 10. Up to 100. And we get a similar behavior, only we're not changing the noise. But this similar behavior, this overfitting-like behavior, still occurs. So let's take a look at some numbers. So here, along the horizontal axis, we have a data set size, and vertical axis, now this is target complexity. This is QF, the upper bound of that summation defining the Legendre polynomial. And so here, if we look here, that's 10. That's a target function complexity of 10. Now again, we're looking at two hypotheses. We're saying E out of G10, degree 10, final best hypothesis, minus E out of G2, the degree 2, final best hypothesis. Now, in the target complexity is exactly 10, well, our complex hypothesis, final best hypothesis, G10, exactly matches the complexity of the target function. And we see here, for a very small number of data points, we're not overfitting. It's not very severe. And that's because the complexity of H10, our degree 10 polynomial, exactly matches the degrees of freedom of our degree 10 target function. And as we increase the data points for that degree 10 target function, it has some noise, but not a lot. We see that G10 is not overfitting. We're in this blue region. But let's say for 80 data points, we're not overfitting, but if we increase the target complexity to 25, we start to overfit severely. This difference is very much larger. And so if we increase our data points enough, well, we're not overfitting up through and including a very high target function complexity because we have enough data points to pay for that complexity of our H10, our degree 10 polynomial hypothesis step. And so on the right-hand side, we see a similar behavior in that we get overfitting, but in this case of overfitting behavior, it's because the target complexity exceeds the capability of our hypothesis set, and this difference, E out of G10 minus E out of G2, is much larger because G10 is overfitting. All right. So essentially, when we look at this behavior of this noise level sigma squared, that's so-called stochastic noise. And when we look at this behavior corresponding to that figure on the right-hand side, that's so-called deterministic noise as the target complexity increases. And so as you increase the number of data points, generally, overfitting goes down, decreases. If stochastic noise goes up, your overfitting goes up. And we saw that in this graph corresponding to stochastic noise. If your deterministic noise increases, your target function complexity increases, your hypothesis set can no longer keep up with the target function's degrees of freedom, and your overfitting also increases. And so let's take a little bit more consideration of these noises. Now, what is noise exactly? Noise is that part of your target function f that your hypothesis set cannot capture, can't keep up. And so essentially, we're taking the difference between your target function and your hypothesis set. And so when we think about this deterministic noise, the dependence on the complexity of the target function where your hypothesis can't keep up, that graph on the previous slide on the right, it depends on the hypothesis set. And it's fixed for a given data point x. But stochastic noise does not depend on the hypothesis set. Stochastic noise is something separate. It was that sigma squared that we talked about, and it's going to vary even for the same x. And so noise is merely just the failure to capture certain aspects of the target function. Now, there are two types of noise: stochastic noise, where there's nothing to capture, and there's also deterministic noise, meaning that you're limited in your ability, the hypothesis set is limited in its ability to capture it. It's out of its league. Its degrees of freedom allow it to bend and twist and fold in a way that the hypothesis set just can't keep up with. Okay. And so your hypothesis does the best it can to fit the noise, regardless of if it's stochastic or deterministic, when you have a finite n. Now, certainly if n goes to infinity, it can keep up. And Herfting's inequality tells us this because you have infinite data resources. And we notice that deterministic noise did not start until complexity 10. Why? Because H10, which resulted in G10, our final best hypothesis, drawn from the hypothesis set of degree 10 polynomials, it has the degrees of freedom to keep up with a degree 10 target function. But after that, it could no longer keep up, and it got worse and worse and worse as the target complexity got bigger and bigger and bigger. So the amount of overfitting increased. And so let's take a look back at our bias variance decomposition. We had our expectation with respect to data set, and then we had instances or data points within those data sets. Now, of course, when we talked about noisy target functions, we added a noise process, our epsilon, which we also called our sigma squared. And of course, we said this sigma squared, this distribution for your noise, it's so-called white noise, Gaussian noise, and it was from the standard normal distribution. So the expectation of your noise is going to be 0. So let's assume that our target function is noisy, and this noise impacts our label. And we're going to redo this bias variance decomposition. So here, I'm going to replace my y value with the definition of the noisy target function. So I say minus f minus our noise process quantity squared. So how I did before, we complete the square, and we add in a plus g bar and a minus g bar. We isolate terms, and we have some cross terms that drop out, and we end up with 3 components. We have the bias term, which is the difference between the best we can do hypothesis-wise, our average final best hypothesis, and the target function. We have the variance term, which says for a given data set, we get a different final best hypothesis, and it's different each time, resulting in a cloud of different final best hypotheses around the average final best hypothesis. And that was our variance, and we said that was a function of how you select the final best hypothesis. And then we also have this noise term. This is our stochastic noise. So this noisy target function changes our bias variance decomposition, giving us a bias, a variance, and a noise term. Now this bias, that's what our deterministic noise is. It's the difference between the best capability of your hypothesis set, your G bar, and this target function. How much can it keep up? So that's exactly what deterministic noise is. And then we also have our stochastic noise term. And so in expectation, epsilon goes to 0. The variance goes down as we increase the number of data points in sample. And bias and noise are inevitable. You can't really change that. All right. So how can you try to deal with this noise? Well, one of the things you can do is evaluate the effect of this noise by simulating or estimating out a sample error, and then check what model choices are the best choice. That's called validation. You can also restrict your hypotheses so that they're not as expressive, because if they're too expressive, they're going to fit the noise in your data. And in doing so, you can lessen the impact of noise and therefore make out-of-sample error a little bit better. That process is called regularization. And so let's take back the example of taking our quadratic target function that was noisy, and we sample 5 data points from it and fit with a degree 4 polynomial. With a free fit, which is the red curve, we get a high out-of-sample error. The in-sample error is precisely 0. It pierces each one of these data points sampled from the noisy quadratic, which is the blue curve. It pierces these data points perfectly. In-sample error is 0. But we see out-of-sample error, the difference between the red curve and the blue curve, is very, very big. But if we restricted it, imagine then if we restricted this degree 4 polynomial to a degree 2 polynomial, we would get a red curve, a fit, that's more quadratic-like in its shape. Now, when it's quadratic-like, we see that in-sample error is non-zero. We've increased in-sample error. We can see that the red curve does not pierce this point. It doesn't pierce that point perfectly. It doesn't pierce this point at all. It doesn't pierce that point perfectly, and it only pierces that first point perfectly. So in-sample error is now increased. But we see that the out-of-sample error is much, much smaller, far improved. This is our restrained fit. And so what regularization does is it restrains the descriptiveness, the complexity, the wiggliness, as it were, of your hypothesis set to encourage it or free it or lessen its chances of fitting the noise in the data. And that's called regularization, which is the topic we will cover next. All right. So with that, that's all I had. I'll end there. And as usual, please stay healthy, stay safe, and I'll see you all on Thursday.